Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on February 5th, 2026, just yesterday. It introduces a framework that enables video generation models to maintain effective context lengths exceeding 20 seconds, which is roughly 2 to 10 times longer than current state-of-the-art methods. The paper is titled, Context Forcing, Consistent Autoregressive Video Generation with Long Context. And, as we'll see later, the implications for maintaining consistency in long videos are really promising. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the central challenge here, known as the forgetting drifting dilemma. The visual panels on the left compare the baseline model against the new approach. In the top rows, we see that baselines with short memory suffer from forgetting, meaning the subject's face changes drastically by the 50-second mark because the model loses track of the identity. If we simply extend their context, as shown in the middle rows, the generation drifts and accumulates errors. In contrast, the bottom row shows that context forcing maintains a consistent identity. The charts on the right confirm this, as the blue line maintains high consistency scores over long durations, while the gray baseline curves drop off sharply. Figure 2 details the training mechanics behind this difference. Panel A shows the standard setup, where a short context teacher trains a short context student. The core problem appears in the middle panel, used by methods like long-live. Here, a long student generates extended sequences, but the supervising short teacher is memoryless, restricted to a 5-second window. This mismatch prevents the teacher from correcting long-term inconsistencies. Panel C presents the solution, context forcing. Now, a long teacher with full memory access guides the student, ensuring supervision accounts for the entire history. Figure 3 details the architecture that supports this approach, split into the training loop on the left and the memory system on the right. On the left, the diagram illustrates the context forcing process, where the student model generates frames while minimizing loss against a teacher, ensuring both models utilize the same history. The right panel zooms in on the context management system, which organizes this memory into 3 distinct parts to handle long durations efficiently. It features a green sync for stability, a blue slow memory that retains key historical frames, and a yellow fast memory acting as a rolling buffer for immediate context. This tiered structure allows the model to discard redundant information while preserving the critical long-term details needed for consistency. Figure 4 demonstrates the real-world impact of this architecture by comparing 1-minute video generations across different methods. The grid shows frames evolving from 0 to 60 seconds. In the second row, notice how the rolling forcing baseline suffers from severe drift, completely changing the visual style from 3D to 2D cartoon graphics after just 10 seconds. The third row, using infinity rope, fails differently. It loses the subject's identity, morphing the purple robot into a white and red character halfway through. Finally, the bottom row displays the result of context forcing. Here, the model successfully maintains both the subject's identity and the background consistency for the entire duration. While Figure 4 showed the qualitative difference, Table 1 puts hard numbers on that performance gap. It benchmarks the 60-second generation task, comparing the proposed student model against baselines like FramePack and long-live. A look at the second column reveals a key advantage. While other methods sustain less than 10 seconds of effective context, this approach exceeds 20. As a result, the Dyno and ClipF scores in the central columns remain stable, even at the 60-second mark, where baselines typically degrade. The final 2 columns summarize this success, showing that the student model achieves superior consistency for both the background and the subject. Table 2 expands the scope, comparing the approach against 3 distinct architecture families: bidirectional models, standard autoregressive models, and specialized long autoregressive models. Looking at the 5-second evaluation columns in the center, the student model performs on par with established baselines like WAN 2.1. But the crucial data sits on the far right, detailing performance over 60 seconds. In this section, the bottom row shows that the method secures the highest scores for both background and subject consistency, surpassing strong competitors like long-live and infinity rope. So, wrapping up, the key insight here is that fixing the teacher-student mismatch allows autoregressive models to finally handle long durations reliably. By achieving an effective context length over 20 seconds, this framework opens the door to generating stable, minute-long videos without the subject drifting or vanishing. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.